everybody. Thanks, Sumit, for inviting me. Thanks, everybody, for staying here. I know I'm the bad guy, holding you from lunch, so I'll keep it short. But what you will see here is a very different type of presentation, and hopefully, some of you will get very interested in the opportunities that the space provides. So I work for General Electric. I've been at GE for 13 years, and we are making a big transformation in the company, moving from an industrial company that makes big turbines or jet engines and so on to becoming what we call a digital industrial company, having a lot of software and analytics expertise thrown on top of the hardware that we sell. So it's a massive transformation of a very large conglomerate. So it's very exciting to be part of that. All right, so what is the industrial IoT? So many of you are probably familiar with IoT, the consumer version of the IoT. What we are interested in is the industrial version, what sometimes we call the IoT of very important things, or the IoT of very heavy things. Some of the industries that we are focused on are aviation, healthcare, and so on. The value proposition of having IoT, having sensors, pulling the data from the sensors into the cloud, doing analytics on it to create a lot of useful applications is abundantly clear in this space. Take, for example, aviation. Does anybody have an understanding of how much of the operating expense of, say, an airline company in India is fuel? 45%. So if I can get you 1% savings on the fuel for one of the big airline companies in India, it's going to directly translate to the bottom line, right? So the 1% savings in fuel probably translates to much bigger value in terms of profitability. So that's jet engines. Healthcare. In the US, 16% of the GDP is healthcare. If I can improve the efficiency of the healthcare system by 1%, we're talking about very, very large amount of money, right? The US economy is about 18 trillion, a few trillion of that is healthcare. So 1% savings on a very large industry like healthcare is extremely valuable. Rail. Indian Railways is one of the biggest railways in the world. What is the average speed of a freight locomotive in India? No. So if you include the wait times, the dwell times, and so on, the average velocity of a freight train is very, very small. It is not like what you normally see, 50 kilometers per hour. It's actually much lower. In the US, with a much larger country, a lot of space to go around, the average freight velocity is only about 15 miles per hour. So if I can get you 10% improvement in average velocity of a freight train, it translates to billions of dollars in extra revenue for the customer. So again, the value proposition is very clear, and of course it applies very much in the Indian context in rail. Power. So we talked about huge expense in fuel for aviation. Obviously the same thing is true for power. And India is a very power-starved country. We import a lot of fuel. So if I can take a small power plant, let's say a gas turbine power plant, with a couple of gas turbines and a couple of steam turbines, small plant, maybe generating 500 megawatts of power for the grid, and if I can save 1% of fuel there, that translates to millions of dollars in extra benefit for the customer. So, and the same thing is true for oil and gas. So all these industries, the value proposition is very clear, and that's really what we are trying to hit. Okay. I would say, broadly speaking, you can think of three categories of applications. If you go to the heavy industry world, you go to a power plant or you go to a refinery, they would not want any unplanned downtime. If they have 1 day of downtime in a large refinery in, say, the Middle East, they're probably losing $100 million a day, right? So being able to prevent unplanned downtime by predicting it in advance is extremely important. So that's what we call asset optimization. Operations optimization, I already gave you a hint of it. Can I improve fuel consumption? And finally, we want to put these things together to create an overall business optimization. How do I dispatch stuff to the grid? How do I figure out what are the market conditions? How do I forecast in advance? And how do I tailor the operation of my plant so that the very expensive equipment lives as long as possible? At the same time, I'm optimizing my business. So combining all these things together becomes very important. And how we do it. So a few years ago, companies would typically know. Take the example of an aircraft engine. I would know, looking at historical data, hey, this engine flies in North America. It's been in service for 2 to 3 years. What we're doing with software and analytics, putting sensors on these engines and collecting the data, gives you a lot more information and a lot more precise. And we want to be able to take advantage of that for our application domains. A single aircraft engine generates about 1 terabyte of data a day, right? And there are 50,000 plus engines out there. So there's a huge amount of data being generated in this industrial IoT space. Not all of it can come into the cloud, right? There's a huge amount of data just for aircraft engines. So we usually end up with a hybrid solution where there is stuff on the edge and there is stuff in the cloud. So that's one difference that you would see quite a bit compared to the consumer applications that we would have talked about earlier today. So you do need an edge device, and then you need obviously a huge amount of power in the cloud. So when you get more precise information, you know, of course, that it's flying in North America, but you know now that it flies 80% in the Pacific Northwest. Very different from flying in Dubai, which is very dusty. You know that the last inspection rating was less than 2, and it's due for overhaul in 7 months. So you're just getting a lot more information that is very precise. Now, what do you do with it? So we call it a model of one. Earlier, we used this data to come up with a fleet level analytic that said, hey, you know what, every 3 years you need to replace this part in an aircraft engine. Well, obviously, the engine that's running mostly in the Pacific Northwest behaves very differently than the same engine running in between Dubai and Mumbai. A lot more hot and harsh environment, different maintenance practices of the operators, things of that nature. So what we end up doing now is, instead of saying, hey, replace this engine part every 3 years, we would have, since we're collecting all this precise information for that particular engine, we would build an analytic that will tell you exactly how much time you need to wait before you replace that part for that particular engine, let's say serial number 501, right? So instead of having a fleet level average, I'm giving you a custom analytic, giving you a precise estimate for when you should do a particular operation. And each one of these operations costs several $1 million to take an engine off wing, do an inspection, remove a part, replace it, costs a lot of money. So I want to do it at the right time, so I reduce my overall expenditure and minimize pain for the customer. And of course, when we gather all this data and put it on our platform, we not only look at this particular analytic, but we think of new services that we can potentially offer to our customer. And so it's in this context that we talk about our platform that we call Predix, which is an industrial IoT platform. Allows you to put all this stuff there. It has a cloud component and an edge component, so that you do the analytics in the cloud, and then you push the analytic to the edge so that you can actually make informed control decisions at the edge. Of course, the more powerful the edge gets, the more learning you can do on the edge itself. All right? So that's really the digital transformation. The cornerstone for the foundation, the technology foundation for this particular massive transformation is what we call digital twin. How many of you are familiar with the concept of digital twin? Okay, not so many. Okay, I'm glad to see a few hands. So digital twin is really, it's a digital representation of a physical system. You have an aircraft engine, I create a digital version of it. But it's not just configuration information of that physical system. It's a continuously learning system. It gets better over time. It's able to make predictions in the future. That's a digital twin. That's where the value comes in. Many of the big industrial players are looking at digital twin as a foundation of their transformation, and so much so that Gartner actually made it one of the top 5 technology trends for 2017. So not extremely well known in the consumer space, but I wanted to use this as an opportunity to tell people about it. So huge amount of value that can be created using analytical techniques, and we will see a lot of changes coming up over the next few years. Just getting into a little bit detail of digital twin, we want it to be useful. GE is a very outcomes focused, business focused company. We want it to be useful. As I said, just like Google and Amazon would like to have a great representation for every consumer, so they can predict exactly what the consumer will do in the future and make the right offers. It's hard to do in the consumer space because these are humans. Here we are talking about engines that people have designed. We know the physics behind the engines. So it should be much better for us to be able to predict how this engine will behave 6 months from now. So we are building per asset models that are continuously tuned as new data comes in, so that the model keeps getting better and I'm able to predict the remaining useful life of an engine, or what will be the efficiency of a particular engine if I move it to a new environment. That is really what we're trying to do. Of course, we want the basic other things to be true. We want to be adaptable. Dan talked about earlier today about how difficult it is sometimes to adapt. If I go and build a digital twin model for a particular engine type, then if I move it from one customer to another, I should be able to very quickly adapt that model to make it work. If I move from one engine type to another engine type, I should not have to restart the whole process, and spend 2 years building model. It should be fast. So adaptability is very important. And we have a lot of technology work to do there to make it actually work. And of course, we need to scale. We need to scale across, huge amount of data and huge number of assets. So that's a digital twin. Let me give you a couple of very quick examples of, the business outcomes. So here is a fascinating example. Here's a wind farm. Wind is extremely important for India. The government of India is putting in a lot of effort to create a lot of wind farms. We see in Karnataka and Tamil Nadu in particular, right? So what's the opportunity by having with digital twin? You want to squeeze every little bit out of the system. You get it for free because you're doing it with software, right? No extra fuel, and any little bit that I get in power goes directly to the bottom line. Probably a huge amount of improvement in profitability for a wind developer. So what do? If I want to get the maximum amount of wind from a wind farm, what should I do? I should orient, the wind direction keeps changing, so I should orient my wind turbines so it points in the direction of wind. That's relatively easy. These wind turbines are not that easy to move, so maybe I need to do a little bit of forecasting a little bit as well, but bottom line, I move it in the direction of wind. That's easy. Then I need to orient the pitch of the blade so that I capture as much of the wind as possible, so the total amount of wind captured is high. That's easy. Okay, a little bit more software and analytics. But now what happens is I notice that, many of you probably cycle, and you see that if you're, cycling with a group, if you're in the slipstream of the guy in front, you see less drag. So it's easier for you to cycle. And, in the Tour de France, for example, they use this in a very big way to conserve energy. Here it's the opposite. If I'm a wind turbine and there's a turbine in front of me, which produces a wake because the direction is in this, it comes to me, I'm not going to see enough wind, so I'm going to produce less power. So that's very bad. So if 20% of my turbines are in wake, what happens? I'm producing overall very little power. So I have to manage this and I have to optimize to get the maximum amount of wind power. What should I do? So here is a trick. Maybe the turbine in front does, kind of behaves in a suboptimal manner. Maybe it kind of steers the wake, it orients suboptimally so that the wake goes off away from me. Okay, so it's off by a little bit, maybe 5%. So it's producing 5% less power, but now I see the full wind, and therefore I produce the maximum amount of power, and collectively we produce more power than before. So what we have here is a network level optimization. I have 50 to 100 turbines in a wind farm. What is the right thing I should do so that I produce the maximum amount of power? I need to be able to estimate my flow field, the wind flow field, if I orient in a particular direction. Remember, the wind speed keeps changing and the wind velocity keeps changing. If the wind speed is not sufficiently high, I don't need to do anything. The wake doesn't even reach the guy in the back. Okay, but if the wind speed is high and the orientation is appropriate, then I have this wake effect. 20% of my turbines might be in wake effect. So I'm continuously doing very, very difficult calculations to estimate what the flow fields will be to optimize, to get the maximum power. It's worth it because even if I get 0.1% extra power, I paid nothing for it. It goes directly to my bottom line, huge improvement in profitability. So that's a beautiful example. Over here, what I have is an example, it's just a video of, we're collecting a lot of sensor data, and these wind turbines might be in remote locations. Connectivity is often sometimes a problem. You might get missing data. When you have missing data, you need to kind of deal with it. Many of you have, I'm sure, who are data scientists here have worked with missing data. Here we're talking about multivariate sensor data, and here we're using deep learning to fill in the missing data. So that's one just one example. Okay. Here is another one. I already gave you a hint of it. This is something that we did in South Asia. We have a small power plant, and can I optimize the settings every hour? So every hour the grid tells me I need 500 megawatts at this particular frequency, and the ambient condition changes. The temperature is changing, the humidity is changing. The kind of fuel that I use changes from day to day. Sometimes I use liquid fuel like diesel, sometimes I'm using natural gas, depending on availability. Maybe half the plant is running on gas, half the plant is running on fuel. What should be the right settings for this collection of equipment, gas turbine, steam turbine, generator, and so on, so that I get maximum amount of fuel savings for the target output? So what we do here is a combination of physics models. We have a thermodynamic model that allows you to model a power plant. As new data comes in, we realize that this model has to get continuously tuned, right? So we do continuous tuning with the new data that comes in, and then run an optimizer on top of it so that we find out the right settings so that you get the fuel savings. So it's really a combination of what I call big data, analytics, which might use deep learning or other technologies, reinforcement learning, for example, and the physics-based models that serve as the core. In some examples, the physics is too complex. We go with completely data-driven techniques. In some cases, the physics is extremely well known. I don't need data at all. I can just do it right. But I still need to tune because the machine can wear over time. So you don't get away. You have to deal with data. And at the same time, if you have the physics, you get an advantage. You get to deal with unseen situations much better if you have a good physics-based model. Here is another example of locomotives. And this could be very valuable for us in the years to come as we are trying to modernize our fleet of locomotives in India. So this is something called Trip Optimizer. How many of you use cruise control in India in your car? Almost zero. How many of you have lived in the US or somewhere else and used cruise control? Lots of you, right? Think of this as cruise control for your locomotive, except it is not about maintaining a constant speed. If somebody is coming from Chennai to Bangalore by the Shatabdi Express, leaving at 6 in the morning, coming here at 10:30, the train really wants to meet the timetable. There's no point getting here half an hour early. Obviously, you don't want to get here late. So if you know the timetable, then you want to really, maximize your fuel consumption, minimize your fuel consumption, because 30% of your cost is again fuel. So what I really have is a cruise control button in that locomotive that allows you to run the train to meet the timetable but minimize fuel consumption. Obviously, very good for new drivers. Okay, very good for new drivers. So this is actually running. It's a product that's been running in the in locomotives or trains in the US for a while, and we have saved a lot of money. You can see up to 10 to 15% of fuel savings, over average drivers. So this is a great product. Now think about how you would do this. I need to create a digital twin of a train, right? I'm trying to optimize a train, so I need to know the load the train is experiencing. I need to have an understanding of the tracks. I need to know the gradation. Effectively, I need to have Google Maps for the trains, right? I need to have Google Maps for the train track, but I need the physics of how the engine operates. I have a control system. So it's like an autonomous car, except in this case, I'm trying to reduce fuel consumption, right? That's really what we have done. So you press that button, the driver doesn't need to do anything. The system knows the map, it knows the signals, it abides by the signal, but at the same time meet the timetable, reduce the fuel consumption. So that's the digital twin of the train that we have built. Okay, here are some other examples. We have a business in GE called Current that looks, think of it as it's a lighting solution with batteries and looks at a city as a whole. So think of it as a smart city type operation. So here what we have on the top right is you have street lights, and GE, as you know, makes light bulbs. How many of you do not know that GE makes light bulbs? Right? Thomas Edison invented the long-lasting electric bulb. So now we are obviously, gone beyond that. We do other kinds of bulbs. We do LEDs and so on. But these, the good thing is that you have a street pole, and the street pole gets power. So that means I can put cameras there and so on. Right? So the whole business is being transformed. So on the street poles, you have cameras, and they're looking at traffic patterns and recognizing various things. So deep learning to for video analytics to recognize trucks and so on. So a smart city can better plan certain things. So on this side, you see that on there I'm recognizing whether it's a truck or a pickup or a sedan and so on. And here is another example in imaging. So GE makes a lot of big equipment. All these parts need to be tested. A single blade in an aircraft engine costs a lot of money. It needs to be tested. Obviously, you don't want to go, you don't want to have any problem with the blade in an engine, for anything that's flying. So what we're trying to do is to automate the process of inspection. So as you see this video here, you have a Spart. It's plant it somewhere and there's an inspection. Instead of doing it manually, you're going to do it automatically. So you have a robotic equipment to decide how to move it and how to position it and when to take the snapshots in time, and then do image analysis of the snapshots to figure out if there is a crack or if there is a defect, and throw it out. So it's a combination of traditional deep learning along with reinforcement learning, combining robotic inspection with image processing. So these are some other examples. I'll go to one other example in healthcare. We talked about healthcare as a huge business. I think a couple of previous speakers already alluded to work in radiology. GE is obviously very big radiology company, and here is an example of something that we are doing with ultrasound. Now, ultrasound is very hard. How many of you have looked at an ultrasound image? If you had a baby, you might have seen it, or maybe they don't let you see it now. But it's very hard, right? It's very grainy. It's impossible. Even if somebody showed me the picture, it's very hard for me to recognize different parts in that picture. It's very hard. So ultrasound is extremely important. Why? Because it's not ionizing. It's not like X-ray. So women over the age of 40 are encouraged to take mammography tests so that they can rule out cancer. Mammography has a lot of problems. One of the problems is that it's X-ray. It's not good. Ultrasound doesn't have that problem. Ultrasound works better for women with dense breast, which is actually higher in the Asian region. So we want to maybe augment mammography with ultrasound so your accuracy levels goes up, and maybe you can reduce certain doses too. So in this case, we are using deep learning to help with various aspects of the radiology practice. So we don't, we really think of it as a huge productivity enhancer for the radiologist. There's a lot of stuff the radiologist knows that will not go into these applications in a very automated way anytime soon. It'll take a lot of time. However, there are lots of things that can be done to improve the productivity. If there is a simple example where I can mark a lesion automatically with the help of an algorithm, then the radiologist, instead of spending 5 minutes looking through that image, is able to do it in 30 seconds or 50 seconds. So the time taken to generate the report per patient goes down very significantly, and that's a huge gain. So this is an example of ultrasound where we are looking at chest wall segmentation so that you know exactly what look like lesions outside the chest wall are not really lesions because they're not part of the breast, and the other ones are important. Of course, we also have other algorithms to actually determine what's a lesion, what's not a lesion, and so on. And one of the big, so we get advantages with deep learning. One of the biggest advantages that we see is what people have alluded to, which is developer productivity. If feature engineering can be taken out, then I'm able to take advantage of it and come up with a good algorithm reasonably fast. The other thing is, we didn't use the word transfer learning so far, but we saw examples of that, in the previous talks. But if I go and learn a bunch of things about ultrasound images from all the images that I've seen, when I go to ultrasound for breast cancer, can I learn from that? Do I need to start from scratch? Answer is no. So developer productivity goes up in a very big way. You also get some improvement in accuracy. So these are examples of digital twins or and AI technology is being used. AI is fundamental to the industrial IoT. If I go to a refinery in, say the western part of India, I might have 10,000 sensors. 10,000 sensors spitting data at like 1 hertz, okay? I'm going to get this data, and I have hundreds of models that are being built, maybe more than that, okay? I need these models to be built automatically beyond a point. Anomaly detection models that are telling me something is going to go wrong. Models that will help me optimize a segment of the plant. Those need to happen automatically. But more importantly, maybe I can hire a bunch of people to build those models on day 1. 6 months later, I'm trying to optimize for fuel consumption. I'm trying to predict for failure. Those failures better not, I should always be ahead of the failures. The models need to be tuned continuously. These are industrial assets. I cannot afford to make mistakes. If I wrongly tag a person on Facebook, okay, no problem. If I, if I say that this jet engine is good and it's not good, big problem. Right? So I cannot afford to make mistakes. So I need these models to be continuously monitored for performance, and I need to tune them so that they are they are above what it needs to be. So continuous tuning is extremely important. You have 10,000 sensors and hundreds of models for one project. You have to do it automatically. So the use of AI is fundamental to the industrial IoT. Okay. So we are building platforms that will help you build digital twins. Now, I mentioned two things that are important. One is that you have physics-based models. I have a thermodynamic model for a power plant. I'm not going to get rid of it. I have to take advantage of it because it will allow me to look at unseen conditions. Past data, I have not seen that. Now I see something new. If I have a good physics-based model, I'm able to use it. So I have to use the physics. So I have a bunch of physics-based models, and of course I have a bunch of input. I put all these inputs together to go and build a collection of models that are important for me. Lifing models that will tell me when something is going to fail. Anomaly detection models saying, hey, something is going wrong now. Optimization models that tell me how to optimize a particular plant. Now all these sounds like really, really big. How can small companies get into this space? So there are two things here. First of all, when you go to a refinery or some big plant like that, there are lots of different problems. And when you, as a small company, for example, take a particular problem and get started at that, it's not a showstopper. You can get started. Okay, so I encourage people to get into this field of industrial IoT because there are lots of things that are completely untapped. The use of data to be able to, have these models that are continuously improving, that will help real operations. Remember, a single day of downtime for many of these guys is millions of dollars. Single day of downtime. So the value proposition is so obvious. If you're able to bring in data with some domain knowledge coming in together to go and build it, you need maybe one domain expert, a couple of data scientists, one data engineer, and a software person, and you can go and make a massive impact to a plant operator if they don't have that kind of model. So that's value. The second thing that we're doing is we're building a platform that we call Predix that's going to be open. So that we can't go and solve the world's problems. Obviously not. We work in certain areas, but it's like a small fraction of the industrial space. So we want to encourage system integrators, startups, other companies to build on top of our platform. So we will provide libraries that are tuned for industrial applications. I'll help you build an anomaly detection model for an industrial use case, whether it's a motor, a transformer, an elevator, or whatever, right? And so you can build on that, and the chances are that you will get better performance out of that. So building on top of the platform is another way for people to get started. This is some more detail, of how we go do this. I won't get into this detail, but let me show you something else. Again, as you can imagine, you've got 10,000 sensors coming from one particular place, at 1 hertz, and you have a large collection of models that need to be built, and you need to integrate data from multiple sources. It's ripe for AI. So what we're trying to do is, effectively build what we might call a learning system. You have an operator who knows everything about a particular asset. It could be an engine. You have a bunch of operators who know a lot about it. That information has to be captured by the system. If you don't capture that information, then it's lost. So you might see the same problem here. You saw it here, you will see it somewhere else. Obviously, you want to use that information. So there's a lot of human knowledge which is there in designers, operators, and mechanics that needs to be captured. Sometimes they will tell you that your system predicted wrongly, and you want to take advantage of that. So obviously, human knowledge is extremely important. Mission critical stuff, that's very important. Obviously, you're going to learn from your own history. Right? You're learning from your own history to decide if something is going to be an anomaly or not. Of course, you're also not learning from yourself, you're learning from similar engines. So if I'm an Airbus, a Gen X engine running between Dubai and Mumbai, for example, then there'll be a bunch of engines like that. I will be learning from the performance of all of those engines. And of course, I want to learn from the entire fleet as well. So I learn from the human, I will learn from myself, I learn from similar engines, I learn from... how do I create a system so that I can put all these together so I don't lose any little bit of information? Finally, we have physics-based models that will allow you to simulate. So I can simulate using a complex physics-based model, and I can learn from that as well. So I can replace the physics-based model with something else, but I can run simulations to test if I should do this or do that. So that's the other thing that we bring to the table. Of course, there's a lot of other stuff, a lot of interest in conversational agents. Obviously, that's another top 5 technology trend for 2017. So we did something with conversational agents where you're talking to a machine. We found it, somewhat surprisingly that a lot of customers indeed want to talk to these machines. They're talking to the digital twin of the machine, and I might say, hey, engine 501, what's the status of your cooling system? And it'll tell me something about the cooling system. And then I will say, hey, I'm thinking of taking you from here and putting you in Mumbai. What will be the status of the cooling system if you go to Mumbai? So we have the digital twin API that will connect to, that converts that to the right model being called, and we get the answer back. So in this case, you see the conversational agent in the back end has programs that will run. These are predictive models or simulations that run. So what will be the performance of the cooling system if this happens? And then I will say, oh, this is not very good. This cooling system performance will not be good in this new state. How should I operate you so I don't have a failure? And then it goes and runs another model. So obviously all the things around conversational agents about context and intent classification and slot filling obviously matter, but you have in the back end databases, knowledge graphs, but you also have a bunch of programs that might run in real time to help you with that. So if you guys have the time, please go to YouTube, you search for Paris Digital Twin. Paris is my manager. We did a demo on stage about a month ago, so you can see what we are trying to do. Obviously, knowledge graphs, we talked about it earlier. Several speakers have talked about it. We didn't talk much about multivariate time series. You think of cars or autonomous cars as kind of the bridge, or smart homes, maybe the bridge between consumer and industrial. Multivariate time series of sensors is fundamental to what we do, right? Fundamental to what we do. That's true for autonomous cars. It's true for us to be able to look at things ahead and optimize stuff. So a lot of work going on in our labs to look at sensor time series. We already talked about deep learning for imaging. Healthcare is obviously a big vertical, but we also do it for smart city, or we do it for industrial inspection. So that's where we are. Where are we headed? I think I can confidently say we are going towards brilliant software-defined machines, no doubt about it. As a company, we're transforming from a hardware company to a hardware plus software company. Machines are getting smarter and smarter. And we want them, not to be fully autonomous until we are extremely confident. There are some cases where it is extremely useful. So we're certainly going towards brilliant software-defined machines. Zero unplanned downtime is kind of the holy grail of the industrial IoT, right? Just remember, for a large operator, 1 day of downtime is millions and millions of dollars. If you're able to impact that even a little bit, you're going to make a lot of money. Zero unplanned downtime. Have the operations always optimized. Right, so you get the maximum out of every asset. Every asset in this case is extremely expensive to build and operate. You want to get the maximum out of it. Sensors, software, and analytics with digital twin will help you do that. We need them to be autonomous and networked. We talked about assets like aircraft engines and locomotives, but think of a network. You have a whole bunch of wind turbines in a wind farm, or you have a bunch of locomotives or trains in a network, and you want to be able to run that network optimally. So these digital twins will start collaborating with each other to decide exactly how they should operate, just like in the wind farm case or in a train network, so that you get optimized. So the digital twins start talking to each other, so you get an autonomous system. Also, you have digital twins within a big asset. You take an aircraft engine, it has a whole bunch of subsystems. Subsystems have a bunch of parts, and you have digital twins for each of these, and you combine all of these together to achieve the outcomes you want. So you have hierarchies of digital twins, and you have networks of digital twins. That's the future, and you'll have these things all collaborating with each other. Some of these twins are not for machines. They could be around business processes. So we talked about a bunch of things with the process, but if you take an industrial asset, the engine comes off wing, it's taken to a shop. People do things with in the shop. They plan when something should be taken off wing. All these are human operations. There are field engineers doing this, and we want to make that as efficient as possible. So everything becomes networked, so that processes will have digital twins associated with them as well. And you want all these now to be driven with intelligence. Every application that we build will have a smarts component to it. The way I like to think about it is that, in today's or yesterday's software practice, we have architecture reviews, we have testing, and we have code reviews, and we have security reviews. In tomorrow's, you're going to have a smarts review. Every application will need to get better over time. If not, it failed, it doesn't go out. That's what's going to happen. And never more true in the industrial than in the industrial IoT. So now you can imagine you have a device, and compute power is improving, storage is improving, communications bandwidth is improving. 5G is going to be so much better than 4G. So you should now imagine, it's very hard to think exponentially, but it takes only 40 steps to go from here to the moon if every step that you take is twice the size of the previous step. Just 40 steps. It's 250,000 miles. Right? Very hard to think exponentially. So you should now imagine that compute power is improving, storage is improving. Imagine you had a supercomputer associated with every device. Imagine that it had petabytes of storage and unlimited bandwidth. What would you do? That's the future that's coming up in the not too distant future, right? Very soon you're going to have that. The supercomputer today, the supercomputer of like what 25 years ago is not even as good as a smartphone, right? So that's what's going to happen. You're going to have a supercomputer with petabytes of storage and unlimited bandwidth on every device. You can do a lot of things with it. So it's up to you guys, people who are entrepreneurs who are coming up with new ideas to think of what those possibilities are, because that is not too far away, right? So that concludes my presentation. Any questions? I'll be more than happy to take. Thank you.